Good morning, everybody, and thanks for joining my session at the DevOps Pro conference. And from wherever you are, of course, nice to have this online session with everybody together. I'm presenting here from the Netherlands, and we're going to talk about fast data. So let me share my screen to start. All right, then. A bit of background about myself. I'm a tech lead or currently lead ML engineer, working with big data, fast data, artificial intelligence, ML, those kind of things, all the interesting bits, so to say. You can find me on Twitter, LinkedIn, so go ahead and would be happy to join to you. So why are we talking about this thing called fast data or streaming analytics? Why does it matter to many organizations? Well, actually, it's not so new, because we have the big data revolution. We've already had this like more than 10 years ago, where somebody invented the 3V model. And basically this model says if there's data that comes to you at a very high volume or a high velocity or a high variety, then we're talking about big data. And then you cannot process that anymore with the traditional technologies. You have to do something special, like setting up a Hadoop cluster, which was back in the days the state of the art. And basically, many organizations only focused on the volume. They gathered many data points. They gathered big data in data warehouses, for example, but not so much about the velocity. And the velocity is like when data comes to you at high speed. But there are currently many use cases where this is actually very interesting. For example, in finance, when you're doing transaction analysis, or in retail, where you're doing clickstream analysis, or in the Internet of Things, where the amount of data that comes to your servers is growing tremendously, because all the machines that are connected to your infrastructure produce a lot of data, and that comes with some challenges, and that's what I want to talk about today. Like, how can you handle this massive amount of data streams? How can you do analysis on that? How can you do even machine learning on that and make it useful for your company? Because there are some common patterns and practices that you can identify when you're talking about fast data streams, and when you're talking about handling massive amounts of event data. And let's start with a bit of a definition, or maybe when are you talking about big data streams, fast data streams? Well, basically, I want to go back to the traditional definition again, where you cannot handle it anymore on one machine or even a couple of machines that are very powerful. So when you have to handle such massive amounts of data that you have to have a distributed data cluster to be able to process all this data, then we're talking about this kind of patterns and practices. Ballpark, like if you already have several hundreds of events per second, you can already start thinking about, that's maybe not so good for me to process that anymore, in a simple simple Docker container, for example, on Kubernetes. But maybe I have to spin up a infrastructure that can handle more load. And if you're going to multiple thousands of records per second, then it's very clear that you cannot process that anymore with the traditional technology. The pattern that you actually see is something like this, because let's say you want to process thousands of click events per second. So you have a massive web shop, and a lot of data is coming to you, and you want to analyze everything that your users are doing online in your web shop. But what you want to do is give them a recommendation. So you want to give them a recommendation for a product to buy. What you could do is then, what you want to do is actually apply a machine learning model on that, because a recommendation is a recommendation algorithm that lives in real time in your data stream. So it has to be real time, because if somebody is interested in something now, for example, a new iPhone, you want to give him that advertisement and that action to that trigger to buy something as soon as possible, because maybe tomorrow or a few minutes after, he might not be interested anymore. So this real time aspect is very important. And it's very difficult to say, okay, where is somebody interested in? because people are doing all kinds of things online. They are browsing, they are clicking all kinds of things, but there is a certain pattern that you could detect. So the first thing is that you want to do is grab all that massive data that comes to you, all these click events, and kind of aggregate it into something which is meaningful. And the meaningful bit is, for example, the pattern that somebody is looking at products that you might have on offer. iPhones or a certain book or something. It doesn't have to be that big, of course. So if you see that pattern happening, then you want to make that recommendation. So that's step 2 of the of this process, is to determine the action. That's where you apply the machine learning algorithm on, and then you produce a notification that can be, for example, an advertisement, or maybe it can be a chat message, or maybe it can even be something else in another backend system. In architecture, looks a bit like this. So you see the same pattern happening here, but then connected to a bit of technology. And what you actually see is here that there's a streaming engine that captures the application flow, and the data itself, the events, are stored on an event bus. So the event data, starting from the raw events, going to the notification events, is all on a message bus. Usually that's Kafka. That's the de facto standard in this kind of application development, this kind of infrastructures. And the application flow is captured in a separate engine, in a separate application, separate piece of infrastructure. For example, Spark or Flink or Kafka streams or something else that might be in favor of you. My examples are in Flink, because that's one of the leading open source frameworks currently in the market. But you can apply the same patterns to basically any other streaming engine. In the second step, then of course you have to apply the machine learning model. So there you have to do some enrichment of your data, because your machine learning model will probably work not on the features that are only in the event itself, but will have to be enriched by, for example, a database that contains historical data, or maybe you want to call an API to make sure that you get all the features that you need to score the machine learning model. So I mentioned already, my examples will be in Flink, but other frameworks exist, like for stream processing, like Spark Structured Streaming. Azure and Amazon also have their own frameworks. So if you're running on one of those cloud vendors, you can also pick their core tools for doing this. So we're going to do a bit of a deep dive into this. What are the exact things that you have to take into account, and what is different from traditional software engineering when you're doing this kind of work? Starting with the basics a bit. One of those applications that you run, so those streams that you want to analyze, those applications that you're building on top of your message bus, are basically jobs. We call them jobs that run on a cluster, on distributed cluster. And the distributed cluster is Spark or Flink or whatever. And you deploy your job to the cluster and have it running there. A bit similar to like traditional big data processing, where you also have a job, but that's usually a batch job. And a batch job has a start and an end. It starts and it's finished, and then it's done. And then you can apply a new job, or you can reuse the same one again and apply some old data on it. And you do it, for example, on a daily basis. A streaming job is never ending, so it doesn't have an end. It's basically continuously processing your data. That also comes with some challenges, because what happens if your data is too big to handle? That's something you have to take into account. A batch job will just be finishing a little later, because it has more data to process. But a streaming job, if it is not processing your data fast enough, it will keep on running, and it will overflow actually in, for example, memory, because it's just not able to capture, to handle all the data that you have. Some examples in Flink, and we're going to explain some of these details in code from now on. A Flink job or Spark job as well is just a Scala or a Java application, runs on a JVM, so you can just write your code in your IDE, test it locally, test it in a Docker, test it even from your own terminal. But once you deploy it, it will run in your big data cluster. It will run in your Flink cluster. Code examples here is basically showing how easy it is to set this up. I'm creating, in the first line, I'm creating a execution environment. Flink automatically recognizes, okay, hey, I'm running on a distributed cluster of, let's say, 10 nodes or 100 nodes. So that's the power that I can consume. There is a certain amount of configuration, of course, in the cluster itself. Like how do you control the parallelism? How do you control the jobs that you deploy to there, etc. But I'm not going to go into the infrastructure details of that. The second statement is very important. We set the event time, we set the streaming time characteristics to event time. I go into that a bit later and explain what that is. And then I'm going to start consuming raw events from my Kafka topic. And there's some building mechanism already. This is the Flink Kafka consumer for strings. So normally, I think you would do like a complex serialization program, maybe Avro, for example. That's the standard for serializing events to Kafka. This is just a string consumer to make it easy. Consuming to topic one with, again, a simple string schema. And then we have a consumer. And then all that is remaining is to connect our our environment to our raw events stream. And then we have a nice raw stream of events coming into our streaming engine, to our job that is running on the streaming engine. I have to be precise for that. Yeah, I mentioned this event time characteristic. Why is it important? Well, what we want to do is want to look at the events in event time, and we don't care about other timestamps. And what's the difference? Well, events are produced at a certain time. For example, the clicks that I mentioned is, the people that are clicking are doing it on their browser, on their mobile phone, for example, or on their laptop. They click it at a certain timestamp. But there is a certain latency, a skew, that happens because the network is a bit slow. So we get the events at processing time a little bit later. There's a delay there. And that's usually not so worrisome. A little delay we can handle. But it is worrisome because events can get out of order because the delay is random, right? It's not something that is the same for every event. So rather than looking at the processing time or the ingestion time of when we get the events, we want to handle events at event time. So we want to look at a timestamp in the event itself called the event time, where these events were actually happening. And that's the timestamp that we will calculate with, basically. Once we have set up a raw event stream, we have to distribute it. So that's also an important aspect, because else your job will be running maybe in a high-performing big data cluster of 10 nodes. But yeah, how does your system, how does your job know how to use all that power, how to distribute the data across your network? In Flink and also in Spark, there's this special function for that, key by. It's kind of a group by function, but then on real data, on live data streams. So you're keying by a certain field in your events. And in my example here, I'm keying by the raw user ID, which might be maybe an IP address, or maybe it's the identifier of a logged in user. That's a good thing to key on, because then your stream will be distributed by that characteristic. So you can actually analyze your data per customer, per user ID. So this is something to realize. So you don't want to key on something which is very generic. You also don't want to key by something which is not evenly distributed, which is where there's data skew. You want to key on something which is meaningful, and also which is causing a good distribution of your data. The other example that I have here in the code window here is that I also want to show that it's very easy to process these kind of streams nowadays. And this is the big revolution, I think, of the past few years with frameworks like Flink and Spark. It's almost like you're working with traditional collections like arrays or array lists in a traditional Java application. You can filter, you can map on these collections basically. Although you have to realize that, of course, what is happening in the background here is very complicated, because there's an enormous amount of data coming at us. The data is distributed, is parallelized, and we're just mapping and filtering and doing all kinds of complex calculations on that. And that the complexity, of course, is handled by these frameworks nowadays. Right. So we have a nice parallel data stream at this moment. So we consumed our raw data and we have distributed this across our network. And now we want to aggregate it. We want to actually just say, okay, all this data is interesting for me, but what I really want to know is, for example, how many pages somebody has already visited, or what the session of a customer was, or maybe a time-based analysis. For example, how many products were sold in the last minute or in the last hour. And that's a very common pattern, and we do that by windowing the data. So you can think of windowing as not a group by function, but then not a group by on a data characteristic, but a group by of time, like a bucket of time almost. And there's three main ways to structure this, to do your windowing. First one is a tumbling window, where you just have a window that follows with another window, and you just define the fixed time duration. So let's say you have a tumbling window of 1 hour, then okay, you analyze the data in that hour. There's also a sliding window where this is similar, but you can have multiple windows that overlap on each other. So you can say, okay, I want to have a sliding window of 1 hour, but I want to analyze it every 10 minutes, for example. And that's interesting, because then you get an average, for example, for this 1 hour, but you get the average like kind of moving across the 10 minutes. And there's session windows, and those are probably the most interesting ones, also the most complex ones, but where you actually define where you say that the start and the end of my window in time are actually flexible. And you can define that by defining what the gap should be between those events. For example, if I've keyed by a customer, then I say, okay, I want to start a new session window when there's an inactivity, a gap of, let's say, half an hour. Okay, then the algorithm knows, okay, now I have not seen events for half an hour. My previous session was finished. I'm going to start a new session. Or you can even look at characteristics in the event itself, like the fields, and read the fields in the event itself and say, if something happens, for example, I know that the event is a logout event, or is a some kind of start or finish of the session, then I'm going to start a new session. And that's very useful if you're doing this kind of things like clickstream analysis, or on the for example, in the IoT, when you're working with machine data, those kind of things. But there's some considerations here. And again, streaming data processing many people find it hard because it's already difficult to grasp these kind of concepts. It's not so difficult, I think, as you might think, but you do have to take some things into account. You always have to think about what does my application now mean, and how do I program it? Because all these windows can be very nice, and you might think, okay, this is useful for my use case. I want to have like a sliding window of 1 day, because that's a good a bucket for me to do my analysis on. And why don't I evaluate that window so I have a slide of 1 minute? Because my slide, I want to have a moving average every minute. You can do that. Technically, that's very well possible. But the thing that you have to realize then is that your window will keep on gathering data and will store all that data in memory. It can offload some data to disk, etc. But still, that's a high performance bottleneck that you have introduced. And you can have all the big data processing power in the world, but you can actually define windows in a certain way that you'll not be able to handle. So smaller windows with less slides, less overlap, etc. are better. But yeah, does that cover your use case or not? That's something you have to realize. And this goes with many of these cases for streaming data analysis. You really have to take into account what are you doing, what kind of performance are you handling. One other thing about Windows, and then we'll stop about this, is watermarks. And this is kind of a unique attribute that you can address to event times. So when you are handling events with event time combined with Windows, because what you have to realize is that if you have defined a window of, let's say, 1 hour, then there's a certain moment when you have to say, okay, now my window is finished, and now I want to calculate that window. I want to, for example, count the number of page visits in that window. But you can never be really sure that this window is actually finished, because some events can still arrive later because of the lateness of events. Now, remember the diagram where I said, okay, the event time takes some time to arrive in our streaming engine. So because there's latency. Well, what if that latency is suddenly 5 seconds, or let's say 1 second? Then what we actually want to do is wait for that 1 second before we actually calculate that window. So you want to wait a little while before we start calculating and finishing and clearing the window that belongs to that hour that we want to calculate. And that's what watermarks are for. Watermarks give you a little bit of slack, give you a little bit of flexibility to wait a little while longer before you actually calculate the event that is already in the past, effectively. Then if some very late event would actually arrive, so let's say you set the watermark to 1 second, and after 2 seconds, there is still an event that arrives that belonged to the previous window already. Yeah, then you can say, yeah, that's too late for us. Sorry, but that event has to go. We're not going to take that into account into our window evaluation anymore. Unless, and that's the final line here, you set the allowed lateness property, and that's a very detailed Flink property already, where you can actually allow even a recomputation of that window, because you want to be absolutely sure that every event that you are that comes to your stream is taken into account. But these kind of properties is what you will be setting, not, for example, for marketing purposes, because that's so important. It's not so important, and it will also lead to more computation, so slower performance. But you can actually look at these kind of properties when you're doing, like, for example, fraud detection. So where you want to be absolutely sure that every transaction that is in your bank is actually taken into account, because if you miss one, that can actually already have big consequences. So in code, how do you define this? Well, remember our previous stream of events, which is already a keyed. Which is a stream of raw events. I created a few other example. I created a new rich stream called here, where we do some enrichment of the data or some mapping and filtering. What we do with this rich stream is first assign the timestamps and watermarks, because we have to tell our streaming engine, our job, where these event times and watermarks are actually located and what they are, because it's not magic, right? So the streaming job that you have defined, that you're programming, does not know which of your maybe multiple timestamps in your event is actually pointing to the right event time, which is there. After that, you do a key by again, and again I have the example of the user ID, and then you assign a window. In this example, I have assigned a standard window, which is an event time session window. So that's what I said. That's one of the most interesting bits where you don't have overlap, but you have a certain gap between the events. So it's not a tumbling window. It's not a sliding window. It's a session window. And the gap that I defined here is 2 minutes or 120 seconds. So that means that if there is no activity during 120 seconds, my event will so my window has stopped, and my event will be starting a new window that comes in. And then I also assigned this allowed lateness property, which I explained earlier, of 2 seconds. So even if event comes in after 2 minutes and after the watermark of, let's say, 1 second, I give it 2 extra seconds of slack to arrive. And if that happens, then I'm going to recalculate the window. And then that's only the definition of the window. And the last 2 lines in this code example are actually the evaluation function of the window, because we still have to do something with that data that we have been gathering in that window. And this example is that we defined a customer session process window function. It's actually a function that knows what to do when the window finishes. And it can be, counting it can be counting the number of clicks in the window, or it can be something very complicated. For example, the machine learning model execution, which we defined. So enriching the data, calling the machine learning model, taking the machine learning calculation score into account, and producing a follow-up notification. And the sync, what is a sync in stream processing? Is basically a wrap up, writing the finishing off the stream. And this is usually a unit function, so that's a function that doesn't have a result in itself. This is the final function in your stream definition, as is here. And here I'm just logging something like a string that may be coming out of my customer session process window function. Right. Yeah. So one other detailed example. So the click watermarks, the click timestamp and watermark generator that I defined here is something that I put into the view here. And because I think this is interesting to show, what I said is there's a certain way that we have to tell our stream where the event time is. And we do that by overriding an extract timestamp function. This is an example of click data. So there's apparently a business class called click, which contains many fields. But the field that we're interested in here is the raw underscore timestamp field. And we're going to parse that in a date time and then get the number of milliseconds from that to get the actual timestamp that we have defined as the event time. And from that moment, if we have done this, our stream knows, okay, we're dealing with event time. So my window evaluations are done by evaluating this raw timestamp field in my events, and I'm going to look at that field specifically. The watermark is implemented by overriding the function called getCurrentWatermark. And this example, it's a relatively simple watermark of 100 milliseconds, where we check if the current max timestamp, which is actually the current timestamp of the current maximum event time, is higher than the previous timestamp. Then timestamp plus these 100 milliseconds. If that's the case, then the watermark will be executed. So there will be a trigger to calculate the event. Right. Let's see how I'm at time. I'm pretty good still, I think. We're going to talk about the machine learning bit a bit more in detail, because one thing you have to realize when you're doing stream processing is that this can also be, let's say, normally when you would say, okay, I have an application and I'm going to do some machine learning. What you will do is you have a data scientist that writes a machine learning model, exports it to a format like Pickle or Joblib, and that file, that machine learning model file, is wrapped in a API that is published somewhere, maybe on Kubernetes, for example. That's a very common pattern. But then you have an API running on a Kubernetes environment, and you have to evaluate that in real time. And if you have to evaluate that for every of the thousands of events that come in per second, even after you have done the window calculation, perhaps, can still be very, very resource intensive. And it can actually be that this is too slow. And I've seen these examples many times, where just wrapping a machine learning model in an API and having that API available on the network somewhere is just not fast enough for real-time data processing. So there's another way to do this, to evaluate machine learning models in real time, and that is to export the models not to a Python-specific format, because usually machine learning models are written in Python, but to a more intermediate format that is language independent, that can in turn also be used by frameworks like Spark and Flink, which are usually Java-based. There's a few of those available. Currently, what's very popular is Onyx, ONNX. Another very important and older and more standardized framework is PMML, and I have some examples of that, but it doesn't really matter. You should just pick one that fits your need. Have your data scientist export your model to this intermediate framework, pick up the framework and load it directly in your stream. So then of course, the benefit of this is that you don't have to go across the network to an API, to a separate system that you don't know what kind of performance it can handle, but you actually have your model readily available in memory in your stream. How does it look like as example? I have an example for PML. This is a piece of Python code. It's not complete, but I think you get the idea that, and it's that these frameworks are commonly available. So people that work with, for example, sklearn have they might have built a logistic regression model. There's one simple extra statement that you have to make in your code to export your model to a PMML file. And that gives you not a pickle file, which is common what I said, but a PML file. So just the representation is different. Looks a bit like this. So this is actually an XML file. So, but you can also export it to JSON. Then it's not called PML, but it's called PFA. Doesn't also matter that much. It's just that these files are interpretable by a framework that is running in your Java stream. And that framework is, in this case, in my example, is OpenPMML. So it's another Java framework, which is open source, which you can use. And for Onyx, there's another one. And yeah, there's this code I want to show. Again, you have to do some work for this, because it's not standard. It's not just one-off line of code or something, but the important line is here the PMML model.evaluate line right in the middle, and before that you just have to capture the input fields, and after that you have to produce the correct target and output fields. That's basically what it is. So a wrap up. I think we have a few minutes for questions left, but first I want to give a bit of a summary of the talk. Talked about streaming data processing, where there's a common pattern. So usually you want to aggregate your data into some kind of a meaningful, more smaller format as well, with complex event. Then you're doing some machine learning on it. I gave some examples of that, and then you want to produce like a follow-up notification. My examples were with the Flink framework, but Spark is also very good nowadays. It did a bit of catch-up on Flink, but it's almost all the features that I explained today are also available in Spark. So if you have already Spark running in your organization somewhere and you want to do streaming data processing, fast data processing, Spark is also a very good way to start. And Kafka, of course, has the de facto message bus. And we talked about some of the common data issues here when you're dealing with basically real-time data and lot of it is related to timing, to the time effect. There's almost a new dimension that you get when you're analyzing real-time data, and the new dimension is time. If you're just doing a query on a database or on a big data cluster, you don't bother too much with the timing aspect. But if you're doing real-time data analysis, you really have to take it into account. How to distribute your data, how to handle late events, what is your event time, how do you handle state and windows, and finally, indeed, how do you execute machine learning models in real time. If you're interested in this kind of topics, these are the basics of these are actually defined in a very interesting paper called Streaming 101. It's on the O'Reilly website. And Google wrote an interesting paper called the data flow, which also is a follow-up on many of these kind of technologies. They picked up these papers and wrote their open source framework for it. There's also a course at the Technical University of Delft called Taming Big Data Streams. I would highly recommend that. It's an online course, so you can do it and actually also get some study points for it. And my source code, and more examples are available on the on GitHub. There's a framework called Sticks, and that contains examples in both Flink and Spark Structured Streaming. And that's it. So I want to thank you first, and then I will go to the questions and see if there are any related questions for me here. And I would say fire away. Let's see. I have a question from Paul Rodriguez. If the volume is too big, would you process data in parallel to avoid your stream taking longer to process data? Yes, of course. That's I think what I try to explain. The key by function is your parallelization function. So if your volume is too big to handle on a machine, this is basically the whole purpose of using a framework like Flink or Spark for big data processing and keying your data, grouping your data on a certain characteristic in your events. And second question is also from Paul. What would you be looking for to evaluate in case you have to decide between Flink and Kinesis? They're a bit different because, first of all, Kinesis is an Amazon specific framework. So if you're not running on the Amazon cloud, then Kinesis is not of much use. Kinesis is a name for two things. It's a name for Kinesis Firehose and for Kinesis itself, and those are the equivalents of Kafka and Flink. But if I would just focus on the difference between Flink and Kinesis, and not take Kafka into account, Kafka is Flink is more powerful. So Kinesis is something I played around with a bit. I liked it, but it's a bit more lightweight framework, which is not a bad thing, by the way, because if you just want to do some simple data streaming, for example, you just want to capture some data from an event bus and write it to a database. You don't need all these complex things like windowing and event time. Maybe you just want to make sure that your data arrives in your database as quickly as possible. So that's not a good thing. That's not a bad thing. So and Flink is more like an all-purpose tool, which is more suited for the complex use cases, and also running on basically any infrastructure, because Flink is an open source framework that you can deploy on a Kubernetes, so on a Dockerized environment, or you can just run it on premise or basically on a Hadoop-based cluster in your cloud. Another question from Paul. What approach would you take to find answers for the 3V model? I assume that you refer to the big data model of the 3Vs. The volume is, I think, is mostly covered by the traditional big data frameworks that do batch processing, such as Spark. I think Spark is the standard way of processing big data volumes in batches. Velocity is what I explained today. So that's the streaming frameworks that you can use for that. And yeah, variety is actually something that is very, very dependent on the on the data that you have, because what happens if you have a high variety of data? I think it mostly comes down to using efficient programming technologies that are able to handle that. So you might have to query multiple databases. You might have to do a lot of data processing to get data in shape and in the right format. And yeah, that depends on what you're already working with. It depends on it's more the question of using the right frameworks and the right programming approaches. To do it efficiently. That's there's not a single there's no silver bullet, right? That's what I meant to mention. There's no key technology or not a key approach to say if you do that, then you're covered for all your data variety. So I hope that answered your questions. If there's any more, then please look me up in the conference or chat to me or find me on LinkedIn or something. I will be happy to connect. And I would like to thank you for your attention and enjoy the rest of the conference. See you later. Bye-bye.